Hi everyone, welcome to our neurotransmission animation project by Annalea, Natalie, Stephen, and Daniel. So first, what we're going to do today is we're going to talk about what happens when a cell receives a signal, a neuron receives a signal, and how it sends it down to the next neuron. Primarily, there is a resting membrane potential that has a magnitude of negative 70 millivolts, and this is caused by a greater amount of positive ions outside the membrane than inside. So what happens when the cell receives a signal is a ligand is going to come in and bind here to the first ligand-gated sodium ion channel. This is going to cause the channel to change shape, and the sodium ions outside the cell, which are in greater concentration, are going to rush in down their electrochemical gradient to diffuse into the cell. This influx of sodium ions is going to raise the cell membrane resting potential to negative 55 millivolts and depolarize it. So when this depolarization happens, it's going to trigger the next voltage-gated sodium ion channel to open, and more sodium ions are going to diffuse into the cell, and this is going to further raise the membrane potential in a positive feedback loop all the way up to positive 30 millivolts. When it reaches positive 30 millivolts, this is going to cause the voltage-gated potassium ion channels to open, and the potassium ions inside the cell are going to diffuse outside along their electrochemical gradients and repolarize and even hyperpolarize the cell to negative 80 millivolts. This hyperpolarized cell membrane is going to be restored back to its resting state by the ion channels in the cell membrane, as well as this sodium-potassium pump. So here we're going to talk about how the action potential moves down the axon along the nodes of Neuron VA. And so first there's going to be the primary influx of sodium, which was just erased, and now this triggers the new influx of sodium at the next location over, which will flip the membrane potential there, and this potassium in green here will rush out of the cell where the sodium just left to repolarize the cell membrane. And this is just going to keep cascading along the axon at the nodes of Neuron VA to the next location and to the next location until it reaches the synaptic terminal, and it will signal to the next cell, which will be covered later in this video. So here we have a graph of membrane potential versus time for a certain point along the axon. In red here we have the resting membrane potential without any outside influence, but then when the first sodium ion channel opens, it's going to raise the membrane potential and it reaches the threshold, which will cause it to spike all the way up to positive 30. Then the potassium channels, ion channels will open, and in green here that will cause the membrane potential to decrease, and finally it will reset back to resting potential.
Nerves communicate with each other via neurotransmitters. These are little chemicals that are found in vesicles on the synaptic side of the cell. Here the signal travels to the end, at which point the voltage-gated calcium channels open, and these calcium on the outside to the inside, which allows the neurotransmitters to be released into the synapse and bind to the ligand-gated ion channel on the postsynaptic side of the cell. Now, omega chronotoxin is a toxin that blocks these calcium ion channels. What happens then is that the neurotransmitters, as a result, cannot be released into the synapse and cannot bind to the receptor on the postsynaptic side of the cell. Omega chronotoxin is an analgesic, which means that it's a pain reliever. So what it does is that it relieves pain, it blocks the calcium ion channels, and thus these pain nerves specifically cannot communicate with one another. Acetylcholine is a neurotransmitter that communicates signals from the nervous system to skeletal muscle cells. Now, as you see here, we have on the outside of the cell acetylcholine, and on the cell membrane the nicotinic acetylcholine receptor. acetylcholine binds to the receptor, causing the response in the skeletal muscle cell and thus movement. For example, in the diaphragm or moving the arm. It's bound and everything's good. Now, the toxin kappa bungaro toxin, what does it binds to that receptor. And if it's not good because acetylcholine can no longer bind to it, so things like neuromuscular paralysis might happen, and through that, because you can't breathe or your heart can't beat, things like that might happen, which might be bad.